Hello, I'm Sebastian. Welcome to Nine Trees podcast. Today, I will summarize and review the book, Reinforcement Learning, 2nd edition, an introduction by Richard S. Sutton and Andrew G. Bartow, is a foundational guide to how agents can learn to make decisions through interaction, feedback, and cumulative reward. Widely used in university courses and research labs, the book presents reinforcement learning as a coherent set of ideas connecting dynamic programming, Monte Carlo methods, temporal difference learning, and function approximation. The 2nd edition updates the field with clearer notation, expanded examples, and broader coverage of modern techniques while keeping the focus on core principles rather than fleeting trends. Readers are introduced to the agent environment framework, value functions, policies, and the exploration-exploitation dilemma, then guided toward scalable approaches for large or continuous problems. The writing emphasizes intuition, algorithmic structure, and the logic behind design choices, helping readers build a mental model of why methods work and when they fail. It is both a textbook and a long-term reference for practitioners building learning systems. I will give you key takeaways from this book. Firstly, the reinforcement learning problem and the agent environment loop. At the heart of the book is a precise way to describe learning from interaction. An agent observes a state, chooses an action, receives a reward, and transitions to a new state, repeating this loop to improve its behavior. The text clarifies the distinctions among episodic and continuing tasks, immediate and delayed consequences, and the practical meaning of return as cumulative reward. It also frames policies as the agent's behavior, value functions as predictions of long-term desirability, and models as internal simulators of the environment. This framing matters because it determines what can be learned from experience and what must be assumed or engineered. A major theme is the exploration-exploitation trade-off, acting to gain reward now versus acting to gather information that improves future reward. The book grounds these abstract ideas in canonical examples like multi-armed bandits and simple control tasks, showing how even minimal settings expose deep issues like uncertainty, nonstationarity, and credit assignment. By formalizing the problem, the reader gains a shared language for analyzing algorithms, comparing approaches, and recognizing which assumptions match a real application. Secondly, Markov decision processes and dynamic programming foundations. The book uses Markov decision processes as the central mathematical framework for sequential decision-making under uncertainty. MDPs encode states, actions, transition dynamics, and rewards, and they make the Markov property explicit. The present state summarizes the relevant past for predicting the future. This setup enables the Bellman equations, which express value functions recursively and serve as the backbone of many solution methods. Dynamic programming is presented as the idealized case where the environment model is known, allowing planning through repeated backups that propagate value information across states. Key ideas include policy evaluation, policy improvement, and generalized policy iteration, showing how prediction and control can be interleaved to converge toward optimal behavior. The text also explains why DP can be computationally expensive in large problems, motivating later chapters on learning from samples rather than full sweeps over the state space. Understanding DP is not just historical context, it teaches the structure of RL objectives and why many algorithms look like approximate Bellman backups. Readers learn to see similarities between planning and learning and to interpret newer methods as scalable approximations of these core recursions. Thirdly, Monte Carlo and temporal difference learning from experience. A central contribution of the book is its clear progression from Monte Carlo methods to temporal difference methods as ways to learn value functions from sampled experience. Monte Carlo approaches estimate value by averaging returns observed after visits to states or state action pairs, making them conceptually simple and unbiased in the limit but often data-hungry and reliant on episode completion. Temporal difference learning blends ideas from dynamic programming and Monte Carlo by updating predictions based partly on other predictions, enabling incremental learning at each step without waiting for the end of an episode. Methods such as TD prediction and TD control illustrate how bootstrapping can greatly improve learning efficiency while also introducing complications like bias and stability. The book discusses on-policy versus off-policy learning, where the behavior-generating data may differ from the policy being optimized, and shows how this affects algorithm design. It also examines eligibility traces as a bridge between one-step TD and Monte Carlo, giving a continuum of update rules that trade off bias and variance. The result is a practical toolkit for learning from streams of interaction in environments where complete models are unavailable. Fourthly, function approximation and scalability to large state spaces. Real-world problems rarely allow tabular representations of value functions or policies. The book, therefore, devotes significant attention to function approximation, explaining how to represent value or action value functions with parameterized models such as linear approximators and, more generally, differentiable function classes. This shift changes the learning dynamics. Updates now adjust parameters that generalize across many states, improving sample efficiency but introducing risks like divergence, interference, and sensitivity to feature design. The text emphasizes gradient-based methods and the importance of aligning learning updates with an objective, laying groundwork for stable prediction and control. It also discusses how approximation interacts with bootstrapping and off-policy learning, a combination that can be powerful but unstable if handled naively. Readers learn why some methods that work well in tabular settings can fail when generalized, and how algorithmic choices and representation choices jointly determine success. This topic is especially valuable for modern applications where continuous state variables, high-dimensional observations, or large combinatorial spaces require generalization. The book equips readers with principles for scaling RL beyond toy domains while remaining aware of the theoretical pitfalls. Lastly, planning, models, and the integration of learning with search, beyond learning purely from real experience, the book explores how an agent can use a model to plan, simulate, and improve decisions more efficiently. This includes the concept of model-based reinforcement learning, where the agent learns or is given transition and reward dynamics, then performs updates using simulated trajectories. The Dyna-style architecture illustrates a unifying view. Real interaction produces data that updates both the value estimates and the model in turn generates additional experience for planning updates. This integration highlights the spectrum between purely model-free methods and purely planning-based methods, showing that many practical systems combine elements of both. The text also discusses exploration in the presence of models, emphasizing how uncertainty about dynamics can guide where an agent should gather data. Planning methods are linked back to the same Bellman backup structure introduced earlier, reinforcing the idea that learning and planning are variations on a shared computational theme. For readers aiming to build efficient agents, this topic provides a conceptual roadmap for when to invest in modeling, how to use simulated rollouts, and how to balance computation with data collection. In conclusion, this book is best suited for graduate and advanced undergraduate students, machine learning engineers, and researchers who want a principled understanding of reinforcement learning rather than a recipe list of fashionable tricks. Readers who already know basic probability and linear algebra will gain a structured view of the field, from problem formulation to the key families of algorithms used for prediction and control. The benefit to a reader's life is practical and intellectual. It teaches how to reason about sequential decision-making, design learning systems that improve through feedback, and diagnose common failure modes such as poor exploration, instability under function approximation, or mismatch between behavior and target policies. Compared to many applied RL books that focus narrowly on deep reinforcement learning implementations, this text is worth buying because it clarifies the enduring concepts that make new methods intelligible. It provides a common vocabulary, a set of canonical algorithms, and the connections among them, enabling you to read papers critically, adapt techniques to new domains, and choose methods based on assumptions. And as a long-term reference, it remains one of the most reliable ways to build durable RL expertise. If you would like to support Richard S. Sutton, you can buy the book through the Amazon link I've provided in a podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.